Welcome. In this lecture, we're going to cover models that are used to predict choke flow performance. So a choke model is an equation or a function that relates the rate at standard conditions passing through the choke. This can be oil or gas. Sometimes you can also use the mass flow, total mass flow, the inlet pressure, outlet pressure, and some characteristic size of the choke, which can be the diameter of the contraction. Choke models, there are two types typically. So they are empirical or data-based, and you have mechanistic models. So in the empirical models, you have correlation, development of correlation based on data. You have some equation that you are fitting all the constants and coefficients with data. And you have the new generation of models that are using more advanced statistical techniques, for example, machine learning, to try to learning from data and developing this relationship. So one disadvantage of that type of model based on data is that essentially you need data, and you should use these models within the range of the original data. You shouldn't use it outside of that range because then it might not be very predictive. The other type of models that are the ones that we are going to discuss today is mechanistic models that are based on taking conservation equations either in differential form or in integral form, and then I apply them to the choke geometry. The geometry that is typically used is this one that is shown here. You have a sudden contraction and sudden expansion, and typically the conservation equation that you apply is the momentum equation, and you apply it between the inlet and the throat. You do that because the pressure, as we mentioned before, the pressure at the throat, there is very little recovery due to the sudden expansion. So then you could assume that the pressure at the outlet is essentially the pressure at the throat. But there are some models that they apply the conservation laws from the throat also to the discharge, and then they try to capture that expansion process. One thing that happens with these type of models is that you need to know how the properties are changing. Typically, we have compressible fluids. We have a gas, for example, that is changing the properties. You have vaporization from the oil of gas. So then you have to capture that process when you go from P1 to P inlet to the P throat. One main issue with mechanistic models is that they are not very predictive out of the box, especially if you have multi-phase flow of oil, gas, and water. So you always need, besides the physical um, equations, you need to have some data to tune your results to the data to make them predictive. So to go through the process to understand better how the mechanistic choke model works, we are going to go through two cases. The liquid case under saturated oil. Then we're going to go to the derivation of a model for the dry gas case. I'm going to give some comments about the multiphase case, and then we're going to have an exercise using the dry gas equation, the dry gas choke equation. So going to the case of undersaturated oil flow, considering this equation that relates the change in momentum that you have and with the difference in pressure along the streamline. And if I integrate this equation between the inlet and the throat, here I have neglected also the friction losses, then I end up with something like this. Because it's a liquid, we have some pressure effects, but essentially the density remains more or less constant, so I take it out of the equation, and then I end up with a difference in pressure 1, and pressure at the throat, which I'm assuming is the pressure out, and I have the difference in kinetic energy, or the difference in the velocity squared at the throat and also at the inlet. So here I almost have what I need. I have the difference in pressure, but I also need the rate at standard conditions. And for that, I'm going to use a mass conservation equation from the inlet to the throat. And then I'm going to relate that to the ratio between the diameters. This is what is called the contraction coefficient. That is the diameter of the throat divided by the diameter of the inlet. And then I end up with an equation that looks like that. The velocity at the throat is equal to the square root of this expression. And then the velocity at 2, I can express it in terms of the local rate, volumetric rate of oil divided by the area of the throat. And then the volumetric rate of oil, I can express it in terms of the standard condition rate of oil times the oil volume factor, VO, at the throat. So and if I substitute all of that here, then I end up with that the rate of oil passing through the choke at standard conditions is equal to that expression. So one deficiency that these models have is that in reality what occurs at the vena contracta or what occurs at the throat, you have lots of recirculations and you have lots of detachment from the wall. So might be that is something like that. And then you have a lot of recirculations here. So the effective area through which the fluid is flowing is essentially less. It's not exactly A2, but it's something that is less. So to capture that effect in the equation and improve the accuracy, then I add this CD coefficient, um, loss coefficient, the flow coefficient, and then this one is simply adapting and reducing the area to account for that effect. It's the vena contracta effect. The effective area is not exactly A2, but it's something less. So the CD typically is a number below 1 and is made to improve accuracy. So you see the shape of this equation. It's essentially that the delta P, which is what is inside here, the square root, is going to be equal to a constant and QO of the liquid at standard conditions squared. So that equation is what I can use for many orifices, many restrictions. For example, for inflow, I sometimes use that equation. And if we see what happens with the rate when we increase the delta P, simply we have a nonlinear behavior, a quadratic equation that is increasing no matter how big we make the delta P, will also make big the QO. And this behavior, we know it's in the kind of non-physical because at some point if we increase too much the delta P, we will have simply that the rate remains constant. But essentially for liquid, the speed of sound in the fluid is actually very high. So you will really need a very high delta P for that to occur to achieve critical flow. So in many cases, simply having this relationship and using it for the subcritical regime, not worrying about the critical, is usually a good approximation. Now let's go and look at the case of the dry gas flow. We have again the same equation applied between inlet and the throat. But now in this case, we have said that V1, because the density of the gas is changing with pressure, and we have a very low pressure of the throat, so then we say the velocity of 2 is much, much higher than the velocity of 1, the velocity square of 2. So because of that, then we can get rid of V1, and then we have like a simpler equation to work with. And then the second challenge we have is that we have to integrate the density with pressure from 1 to 2. And we have to know how the density behaves with pressure. So an assumption is typically made is that you assume that the process is adiabatic. So I have no heat exchange between 1 and 2, and the process essentially is reversible. And if I use the gas, I use an ideal gas assumption, so this gives the following relationship between pressure and density. The pressure and the density are related like that, pressure times density to the power of K. K is the ratio between the specific heat of the gas at constant pressure and the specific heat of the gas at constant volume. Is a gas constant, and that is equal to a constant. So this remains constant through the contraction from 2 to 1, from 1 to 2. So then if I use this now, I can express density as in terms of P, and I can substitute in the equation, and then I can make the integration. And then to get rid of the C, I apply the inlet conditions. So C is a constant, but so I apply P1 and the density in 1, so then I will be able to find out how much is C. Another thing I made here is that I introduce the pressure ratio, which is the pressure at the throat or at the outlet divided by the pressure at the inlet. And then I end up with this expression now. So you see it looks already almost like what I need, but I have the pressure. Instead of having the pressure difference, I have the pressure ratio, but doesn't matter. I have the inlet and the outlet pressure, and then I need the standard condition rate. So here I made some more changes. So I substitute the density with the real equation of state using the C factor, and then I substitute that. And then I say that the rate, the velocity at the throat is equal to the local volumetric rate of gas divided by the throat area. And then I can relate that. I could have done it with the gas volume factor, but I decided to use this relationship that is mass conservation. You have only one phase, so you have just dry gas. So you can say that the local rate of gas at the throat times the density of the gas at the throat is equal to the standard condition rate of gas times the density of gas at standard conditions. So if I substitute that, then I end up with this equation, which is already very close to what I need. And then to express the density of the throat, I can use again this expression, this adiabatic expansion, and then I have to substitute again I don't want to have density of 1 there, but I want to have essentially Z and temperature. So if I do all of that math, I end up with an equation like that. I also correct with the flow coefficient to capture this effect of the vena contracta. So I end up with an equation like that. Significantly more complicated than for liquid, um, but is it's because the gas is compressible. So now let's see what that equation. I'm going to try to plot what that equation gives in terms of delta P with respect to Q of the gas at standard conditions. So this equation has again like a quadratic behavior, like second order polynomial. Okay, but at some point, if I continue increasing the delta P, it has a behavior like that. It's simply like a mirror. Okay, and then it goes to 0. We know that that's not physical, that in reality when we reach certain point, so then I will have simply a constant rate. That's when I reach, this is the subcritical, and this is the critical regime, in which no matter how much I reduce, remember this delta P is equal to P1 minus P2, then I'm saying that P1 is constant. So essentially to change the delta P, essentially I'm changing P2. Okay, and here it seems that I change it all the way to 0. Okay, so that means that the delta P is maximum. Okay, so this is not what this equation gives, but if you were going to plot that equation, the equation actually goes through this dotted line, which we know is not realistic. So one way you see here that this has a maximum point before it starts going down. So one way I have to actually find the critical point, that's exactly where this curve changes, the maximum of that curve, is to find out that when the derivative of QG with respect to delta P, or actually with respect to P2, is actually equal to 0. That's when when I have this flat point here. And if I try to apply that using to that equation, then I will end up with this criterion that's saying that the Y critical occurs exactly when you have is equal to this number, when you have this gas constant K. And this number for K is typically something that is maybe around 1.2, 1.3. So this tells you that the Y critical is something like 0.5, approximately something like 0.5. So that was a dry gas equation, and that's what we're going to use a bit later, as it's slightly different modified version of that. If you see here, this is all using SI units. So here the pressure is in pascals, the area is in meters, uh, pressure ratio well doesn't matter what I'm using, but yeah, the temperature should be in Kelvin, but in reality we're using units which are kind of a more practical SI units. Okay, we are using bar, we are using Celsius, we are using this rate should be in standard cubic meter per day, not cubic meter per second. Okay, so we know we have to add some constant to this equation to be able to change the equation, the units, to convert between the units. But now let's go a bit as a detour. We're going to go through a choke model for multiphase flow. So there you have your momentum equation for gas-liquid flow. We're assuming that the liquid is made up of oil and water. And we are not going to go, we will have later some lectures on multiphase flow, but see that the delta P now, you have some contribution from the gas. How is the velocity of the gas changing? And how is the velocity of the liquid changing? And you have here this parameter H, which is essentially is the holdup. Okay, so H is how much of the phase is being occupied in the cross section of the choke or of the pipe by liquid or by gas. Okay, so the H is, for example, the area, the total area, and the area of the gas. Okay, so that will be the holdup of the gas. It's how much is being occupied by the gas. And we will see this in a later video. So you have that equation that you have to integrate. One assumption people typically make is that the two phases go at the same speed. So then you can have just one velocity and it's a bit easier to integrate. Another assumption they make for the properties, for example, is that the density of the gas is changing, but now you haven't because it's expanding with also with liquid. So then you and oil and water. So then you have some slightly different exponent. It's not k anymore, but it's this, and this is the mass fraction. This x is the mass fraction. Mass fraction. Typically is at the inlet. Some people assume that the mass fraction is not changing along the choke, so that makes slightly more difficult to integrate the choke model. Other people, they simply apply the energy equation along the path. So the energy equation, you have no heat transfer, you have no work. So essentially, the energy of the fluid is all the components of the energy of the fluid, they remain constant along the streamline. Okay, so you say that the enthalpy of the mixture, it should be equal to, in this case, the kinetic energy variation of the three phases. Okay, so that could be another way how I derive. So it's much more complicated when you consider multiphase flow because I have to deal with three phases. I have to make some simplifications regarding how these phases are transported, and then I have to make some simplification about the properties. Again, one simplification is used. Well, the densities of the liquid remain constant, but the densities of the gas, they are changing with some expansion. So now let's talk about the exercise, and we're going to use this model. It's a dry gas, and we're going to dry gas is very similar to this model here, but as I mentioned, we need to have some constants to be able to, that is going to give us in the units that we need. Okay, so we are going to work here with standard cubic meter per day for the rate standard conditions rate of gas. We're going to work with temperature, which is in Celsius. We're going to obtain the set from the standing chart, which we are going to use this Jarl Harborough correlation. And we are going to input this the pressure in bar. Okay, so here we have our Excel sheet that we have. Here you see the CD, the discharge coefficient. It's less than 1 because we know we have this Vena-Contracta effect. The gas gravity, which is the molecular weight of the gas divided by the molecular weight of air. And we know where that comes in the equation. That comes because I need this molecular weight. Okay, and also I need the C factor, so I also for that I need the molecular weight. Then we need the K of the gas, and for that we're going to use an expression that that is given here. This expression is typically used for compressors, for gas compressors, so I took it from there, but you might use the K for the gas that you have. Okay, so we're going to use that. And that is only a function of the specific gravity. So we're going to take here, this is going to be a function, it's in the function I call it K, adiabatic. And this K is going to be only a function of the gamma of the gas. Then the inlet temperature, 70, and a critical ratio, we know that equation, it was given here. So that's, if I have K, I can calculate the critical ratio. And that critical ratio, if I go Alt F11, okay, you see here I go to the module that contains the choke equations. So then I have, first I have K adiabatic. So this was that expression that I showed you before to calculate K of the gas with the specific gravity of the gas. This is the critical ratio. This is the same equation that I have here. Okay, so let's use that equation with the K to see more or less where is going to be this Y critical ratio. That depends only on K, surprisingly. Okay, 0.5, exactly there. And now we are asked to calculate what is going to be if I have these conditions on the choke P1 250 bar, P2 200 bar, and a diameter of 15 millimeters, what is going to be the rate passing through that choke according to this model. Okay, so let's see this set here on that model I'm obtaining with the equation, the function we have used in previous videos, this factor standing, in which I input pressure, temperature. Remember, for the chart I need is the reduced pressure and the reduced temperature, so I need also the critical pressure and the critical temperature. I'm doing that using um, using a correlation developed by Sutton in this paper that he has. These are the two correlations that are used. Okay, that if you have the specific gravity of the gas, then you calculate the critical point of the gas. Okay, and the unit here, this function is actually flexible if you want to work in field on metrics. So, but this unit should be 2. So we're going to use that function that we have shown before. And here you have the function that we use for to calculate the rate. I call it orifice rate metric, and here is using all of this input. The CD, the diameter of the choke, inlet pressure, outlet pressure, is using a specific gravity of the gas, the temperature at the inlet, and then the adiabatic constant. Okay, so let's see that equation, how it looks like. It looks slightly different than the one that we have presented here. It looks like that. Well, the equation that we were discussing it looks like that. So it looks a bit different, but it's simply because you need to have these constants that they are changing between units. Okay, so they have grouped, they call CN, and then you have CS. Here you have the CD. This S is the unit conversion constant, but it's essentially the same equation. So, but that's what we are using here. And this equation, I took it from a book, Gas Production Operations by Bex. Okay, you can also have, if you want to change it for field units, you also have it there. So you see here, we have, this is the unit conversion coefficient. This equation uses actually in kilopascals, not in bars, so we need to do some conversion here is the conversion to kilopascals. We calculate the Z at the inlet, and then after that I determine if I'm in the critical. Okay, if I am in the critical, then I should use simply the rate doesn't change, and I should use the critical ratio. Okay, because here the rate remains constant. So simply at that point, simply I should use for all of these points that you should use the critical ratio. Okay, and then I apply the orifice equation. So let's do that. Let's first, we have the two pressures, diameter, and then we calculate the ratio. Remember, this ratio should be always less than 1, which tells you that the pressure that you should divide is the pressure at the throat or the pressure at the outlet divided by the pressure at the inlet. Okay, so that gives you a pressure ratio of 0.8, which is actually bigger than 0.5. So that means actually that I should have subcritical flow. Okay, so then let's here call the equation, it's called orifice. And it's called orifice because I can use that equation also not for a choke, but for an orifice. It's exactly the same. The CD is here, and that I block. The diameter is here. Pressure 1 is here. Temperature 2 is here. Specific gravity of the gas is here, that I block. Temperature 1 is here, that I block, and the K is here, and also I block. Okay, so you see that the rate is 663 0.6 or 63,000. So now let's make keeping P1 trying to make the performance graph. We have P1 constant, and then we are reducing P2, keeping the same diameter of the choke. So we take that let's do it in steps here. 250, let's use 250, and this one will be 250. So here I should be 0, but then let's go in steps of 50, 200, 150, and so forth. Here I should use the same all the way to 0 outlet pressure. And we know at some point it should remain constant, the rate. Okay, here I gave 1, and here you see between these two, so this one, all of these three, they are subcritical because the y is greater than this one, but all of these should be critical. Okay, and then we see what happens with the rate. You see here is increasing, and then it remains constant at 804. So you see actually that this choke, this is the maximum rate can pass through that choke. And let's see how the plot looks like. Dx is the rate, that's what we have been using so far, and the y is here it should be the delta p, right? So we need one more column with the delta p. Zero, and then it's increasing all the way to 250. That's the biggest value it has. So then I'm going to come here to this plot. Yeah, and I shouldn't use A, but I should use column G. Okay, so you see exactly what we were expecting, that the rate is essentially increasing in a nonlinear way, and then it becomes constant until the maximum delta P that I can achieve. Now, what will occur if we change the choke diameter? Let's say we open the choke now. Let's say we have now an opening of 30. Okay, let's see what happens. Well, essentially, you see now the limit rate was 600,000 before, and now is 3 million. Okay, so it almost increased significantly the choke rate. And if we use a smaller value, for example, if we use 10 millimeters instead of 15, so then the curve moves to the left, and now the maximum is not anymore 600,000, but is 350,000. So this was an example about how to use the choke model. You can also see what will be the effect of changing the inlet pressure. What effect will it have on the curve? And also you can use this to try to in a different way. Here we have used it for metering in a way. We have inlet pressure, outlet pressure, and diameter, so we want to find out the rate, but we can also use it for design. We have some rate and the delta P, and we want to find out which diameter to use. And we could also use it to predict performance. So we have a rate, and we have the pressure and the diameter, and we want to find out the outlet pressure. So I suggest you to try those options, because then you have to use the model in a slightly different way, and probably you have to use the solver to do some iteration on the equation.